Huh. Can we start, sir? Can we start, sir? रुक जा।
Good morning, participants. Welcome to all to the second day of 2-week certificate program on cybersecurity and digital forensic. I welcome you all once again warmly to this session on mathematics. So this session will be taken by Dr. Alpana Mishra, and she will be delivering her talk on number theory and some other mathematics prelims. And before I hand over the mic and platform to her, I would like to introduce Dr. Alpana Mishra to you all. Dr. Alpana Mishra has completed her B.Sc and M.Sc in mathematics from Dr. B.R. Ambedkar University, Khandari campus, Agra. Her PhD is in the field of mathematical modeling with a specialization in mathematical biology with a scholarship from Department of Science and Technology. She has published her research work in various national and international reputed journals and also presented her work in different national and international conferences. She has a total experience of more than 14 years in teaching and research. She's active in teaching various courses like B.Tech, B.Sc, B.Ca, M.Sc, M.Phil, and MBA classes. Initially, she started as a guest faculty of mathematics at Dr. B.R. Ambedkar University, Khandari campus. Then she went to join Banasthali, Rajasthan as GRF. And then from 2014, she is associated with Chadha University. And at present, she is member of Center for Cybersecurity and Cryptology, Chadha University. So, ma'am, with that, we welcome you to deliver your lecture on number theory. Please welcome her.
Thank you so much, Dr. Venus. Thank you so much. We all know that cryptography is basically can be played with the help of mathematics very well. So I just wanted to give some brief about the number theory actually, because it seems someone we all are doing number theory since from the very beginning when we started studying. So let's just start to play with the numbers first. And after that, we will be considering few concepts which may be related to hardcore mathematics and which will be the part of the abstract algebra, but it will be taken later on. So initially, I'm going to start with the number theory here. So, we all know that how the division has to be made. We are having two numbers, A and B, and whenever the number A is getting divided by B, so you will be able to get some remainder and the quotient as well. So this is the basic thing, because whenever we are dealing with the numbers, we have to only consider four operations like addition, subtraction, multiplication, and division as well. These four things are the very basic operations which has to be considered everywhere, even in the daily life also. And the beauty of algebra is basically totally dependent upon these basic operations too. So whatever we are going to consider here, it is basically all dependent upon this division process. Like addition is also included here. And I need to tell you this at the very beginning that whenever we are dealing with these four basic algebraic operations, out of these four, we are going to consider two as same, like addition and subtraction has to be taken same. And this multiplication and division has to be considered as the same process. Because, when we are adding two numbers A and B, it will be reflected as A plus B equals to something like equals to C. But whenever I'm doing A minus B, so it is also reflected as A plus of minus B, which is also the adding of a positive number A to a negative number minus B. So we generally consider this addition and the subtraction, both are the same operations. Same way, if I'm having any number like 4, I'm trying to multiply this number 4 by 2. So it seems like multiplication 4 into 2 comes out to be A. But what happens actually, say for example, I can multiply 4 by 1 by 4 also. So it seems like, division and multiplication to be the same number. So both will be same. So, in general, after that, we are considering that addition and the subtraction as same, and the same way multiplication and the division is same. Am I audible?
Yes, clear.
Echo is happening actually. Echo somewhere, echo is coming. Echo is happening actually. Am I audible?
Yes, audible.
Okay, now it is fine, I think. Okay, so we have to start this division algorithm first. So what we are having this division algorithm, we have done the multiplication very well from our beginning classes also, right? I just multiply, say for example, I have written an example also, like I have dividing my 17 number with 5. So 5 times what we are going to do, 5 into 3 is equals to 15 and the remainder has to be taken as 2. So 17 can be written as 5 into 3 plus 2, in which 3 has to be treated as the quotient and 2 is treated as the remainder. We have done this division from our early classes also, but we don't know that it is having a very specific name which is known as the division algorithm. And this division algorithm is basically will be treated as the basics for everything. right? So what we are having here, like this division algorithm, this simple multiplication, the simple division has to be like whenever we just wanted to give the abstract notation of these to this notation, to this division. So it seems like A equals to BQ plus R. I have used this notation A equals to BQ plus R, in which A is getting divided by B, Q comes out to be question, and R will be taken as a remainder. So that's why I have taken this C. You can see that one example also, whenever I'm taking A equals to 17, B equals to 5, whenever 17 is getting divided by 5, so the remainder will be 2, and the question Q is we are getting as 3. The same way, if I'm having A equals to minus 23, which seems like a negative number here, and B equals to 6. So if I divide 23 by 6, so it will be like 23 can be written as 6 into 4 comes out to be minus 24, plus 1 will give you minus 23. So this is basically the division algorithm. Why I'm taking this division algorithm? Because, when you start doing that, the series is somewhere dependent upon the cryptography also, right? So in the cryptography, what we are trying to do, we are simply trying to consider one message. It will be encrypted into some another form. Then after that, the another person, whenever this encrypted message has to be sent to the another person, this has to be decrypted again. So what we need here actually, whatever the help we are taking just in order to encrypt this message, the reverse process has to be used there. So what we are going to use actually the inverse process, right? If I am decoding any function, any text here by using some function, so after that, when it reached to the destination point, we have to use the inverse function again to get it back the original message. So, the whole process is actually, just to find out the inverse, and this division algorithm and whatever the concept we are going to consider after that, it will be totally considered as a basic for that, inverse issue. So, this division algorithm will also be a part of the same process. So that's why we are doing this division algorithm here. So this is what we have about the division algorithm. GCD, we all know that what is this GCD actually? GCD has been considered as the largest factor of two number. Like I'm having any two numbers A and B, and what is the GCD? GCD can be considered as the common factor to all, the greatest common factor to all. Say for example, I'm having two numbers like 98 and 56. I have written over there. So the highest common factor in between 98 and 56 is taken as the 14. So this is GCD. GCD is going to play a very important role as well while we are doing this cryptography thing. So it has to be considered here. That I just wanted to recall it here. Prime number, we all know that what is prime number. Prime number is nothing like, it is simply any number which can get divided only by one or by itself. These two things are going to play a very important role after that whenever we start doing that cryptography. So these things has to be considered later. Now let's just come to the Euclidean algorithm, which is basically can be considered as the application of division algorithm itself. See, again, I already told you that GCD and prime numbers and this inverse thing will going to play a very important role here. Next session will be taken by Dr. Shrikant. Actually, he will be telling you better that how these things has to be used. And when the process starts, like, we keep defining that how these things are getting involved with this encryption and decryption process. So what we are having here, what this Euclidean algorithm says, this Euclidean algorithm is considered as the application of division algorithm. That means what we are going to do here, we are going to use this division algorithm repeatedly in order to find out the GCD of two numbers. Like I'm having two numbers A and B. I just wanted to find out the GCD of these two numbers. See why I'm trying to GCD actually, because later I have to consider this GCD as one every time. So I have to adjust myself to the prime numbers. So this is the initial process what has to be considered here. So like I'm having two numbers A and B, I just need to find out the GCD of these two numbers. So I am going to use the division algorithm in the repeated manner. So what I'm having here, A and B, the GCD can be written as A equals to BQ plus 1 R1. BQ1 plus R1. So what I'm having A and B. When I divide A by B, so quite obvious, I'm going to get some question and the remainder as well. Let's just nominate this question and remainder as Q1 and R1. Because why I'm taking this Q1 and R1, because I just wanted to make a difference between the next getting question and remainders. So that's why I'm just nominating it as Q1 and R1. So A equals to B of Q1 plus R1. Quite obvious, if you are dividing A by B and whatever the remainder you are getting, the remainder must be from 0 to B, because the B is the number what has to be considered as a B is A is getting divided by B. So what we are having here, let's just take this A equals to BQ1 plus R1. Now what happened when we are using it in the repeated manner? Let's just forget about this A now. Now this B will take the place of A and R1 will take the place of B, right? What we are having initially, we are having A and B. We are implementing the division algorithm and we are simply writing it down as A equals to BQ1 plus R1. Now in the next step, A and B, it has to be replaced by B and R1. Like B will take the place of A and R1 will take the place of B. Same way, I am dividing my B now R1, and by using the same division algorithm, I'm doing this B equals to R1 Q1 plus R2. Next step, when I go to the third step, I will repeat the same thing, but now my R1 basically has been treated as B and R2 has been treated as, like R1 is treated as A and R2 is treated as B. So now I'm going to divide R1 by R2 in order to get new Q3 and R3. The same process will get repeated till we are getting 0 as a remainder. When we get 0 as a remainder, so just previous non-zero remainder will be considered as the GCD. If somehow the process is not very clear here, let's just take one example in order to understand this. So let's just take two numbers, A as 2520 and B as 154. When I'm dividing A by B by using the division algorithm, so it will give me this thing, 2520 equals to 154 into 16 plus 56. Now, the 16 has been treated as my Q1 and 56 has been treated as my R2. You just seen it before. A equals to BQ1 plus R1. So my Q1 is 16 and R1 is 56. Now, what I told you that B is going to take place of A and R1 will going to take place of B. And it is, in the computers, it is a very well-defined algorithm. This can be computed very well with the help of the computers. So what we are having here now, I'm going to divide my 154 by 56. When I'm doing it, 154 comes out to be 56 into 2 plus 42. So my new Q, that means which is considered as Q2 here is 2. And now my remainder will be 42, which is nominated as R2 here. Now in the third step, I'll again consider my R1 and R2. R1 is treated as my new A and R2 is treated as my new B. So I'm going to divide my 56 by 52. While I'm doing it, I'm again getting some quotient and remainder, which is 1 and 14 respectively. In the last step, as you can see that now I have to divide my 42 by 14. So when I divide my 42 by 14, it will give me the remainder as 0. So I have to stop my process here and I'm going to consider the previous non-zero remainder as a GCD here, which seems like 14 here. So the GCD of 2520 and 154 comes out to be 14 here. This is the process of finding a GCD of two numbers. The numbers may be very large, so a proper algorithm has been defined in the computers, so it can be well calculated. Now I'm going to show you the reverse process of that. That means if I'm having some GCD available to me of any given two numbers, so by using the same process what I have done in the earlier step, I'm going to use it in order to write down this GCD in form of some linear equation. This is known as the extended Euclidean algorithm actually. That means what I'm going to do, I'm going to write down my GCD into the form, as you can see at the bottom of my slide, SA plus TB. A and B, the numbers which are supposed to take the GCD, and this S and P will be our new scalar values. So that means this GCD can be written in this particular linear equation form. How I'm going to do it? Like in the previous step, I have taken this 14 actually, 14 as the GCD. So from the I'm going to take the third line here, 56 equals to 42 into 1 plus 14. So 14 can be written in terms of 56 and 52 as 56 minus 42 from the third equation, right? 14 equals to 56 minus 42, as you can see here. Let me just do it. See, from this equation, you can see here, 56 equals to This is the value what I'm going to use here. 14 equals to 56 minus 42. Now, before 14, my remainder was 42. So I'm going to replace this 42 by my new AB, what I have calculated earlier. So 42 is getting replaced by 154 minus twice of 56. 56 is getting 2 into 56. It seems like 2 into 56. So now you can see in this equation that 56, 1 into 56 is available, 2 into 56 is available. It will give you 3 into 56, thrice of 56 minus 154. Now before 42, I'm having the remainder as 56. Now 56 will be getting replaced in terms of the original A and B. That means 2520 and 154. And you can see here that after simplifying it, I'm getting 3 into 2520 minus 49 into 154. So my S and T will be taken as 3 and 49. This is known as the extended Euclidean algorithm. And what is the use of this extended Euclidean algorithm? Actually, as I told you that we always need some inverse function for the same. So this extended Euclidean algorithm is going to be used in cryptography just in order to find out the inverse. It will be clear later, like when I'll be taking the another session for the same. So I will make it clear that how I have used this Euclidean algorithm in order to find out the inverse of two numbers, inverse of any number. So this is your division algorithm and the extended division algorithm. Let's just come to this modular arithmetic actually. If I talk about this modular arithmetic, so, we play, we have played it well in our earlier days. Like what we are having this modular arithmetic. This modular arithmetic is we use it every day, daily time. I'm going to give you a very simple example in which we are using the modular arithmetic. And what is the easiest example? I can just say, for example, today, like it's Tuesday. And I'm asking you that after 25 days, what day it would be. So quite obvious, we are not going to count it on our fingers, like what day it would be after 25 days. So as I know that, this is the best example, what I can give you that, how we can use this modular arithmetic. Like 25, I am going to count the day after 25 days. So, and I know that within a week, there are 7 days. So I'm going to divide my 25 by 7. That means I am implementing my division algorithm here. So I'm dividing my 25 by 7. So I'm having the quotient as 3 and the remainder as 4. So how much remainder I'm having here? 4. What I'm going to do? I'm going to add 4 to the Tuesday. Tuesday, मैं कितना add कर रही हूँ? I'm adding 4. So I'm getting the Saturday here. So after 25 days, it would be Saturday. So this is the application of the modular arithmetic. And this is not only the one application. There are a lot of applications. In so many ways, we can use it. And in very big things, I mean, it is going to be used. This small mathematics is going to be used in so many big things. This is the easiest example what I can give you. So this is the use of the modular arithmetic, actually one of the basic example. And we have already know that because it is an application of the division algorithm. So A equals to, earlier we have used the notation BQ plus R. So this is exactly the same, QN plus R. Actually, I just wanted to make you, understand that what is this modular value. So I have taken this modular value in general as N. Like what I'm having, say for example, this modular value comes out to be equals to remainder when I'm considering some cap over there. Like what I have done, I have taken 25, I'm dividing 25 by 7. The remainder I'm getting as 4, right? So this modulus value is basically 7 because after 7, I'll make the entire term as 0. What I'm doing actually, like 7 into 3 comes out to be 21. 7 into 3 equals to 21. So if I'm working, about this modular value 7, so this 21 will make it, after 7 पे आपको क्या दे देगा? It will be 0. 7 plus 7 equals to 14. It will again give you 0. Then again you are adding 7. It will be 21, giving you 0. So that means what this modular value is doing, it is, putting a cap over there for a particular number. So this is the modular value, what we generally consider as mod value, and we just nominate it as N. That means any number A, you can see here I have written A equals to R mod N. So if I'm using A is getting divided by N, the remainder what I'm getting as R. So A will be coming out to be equals to R under modulo N value. Say for example, like I have taken 3 mod 2. So 3 is getting divided by 2. The remainder comes out to be 1. So I'm going to write down 3 mod 2 equals to 1. Same way, if I'm taking 11 mod 3, so I'm dividing my 11 by 3. So it will be like, 3 into 3 equals to 9. So how much remainder I do have here? 2. So I am writing it down 11 equals to 2 here, because it is written since 11 equals to 3 into 3 plus 2. Same way, if I'm having 62 modulo 85, you can see here that 685 is greater than 62. So if you just wanted to write down the 62 in terms of the division algorithm, so it seems like 62 equals to 0 into 85 plus 62, right? So in that case, 62 will be coming out to be 62 itself. So in general, what we are seeing, it will not create any difference between these two. Either you can write down A equals to B mod n or A mod n equals to B. It will give you ultimately the same value. So A equals to B or R, what you have seen earlier, mod n, it will simply replicate n divides A minus B. That means the remainder comes out to be 0. If I'm having a much bigger number, or two numbers are giving as a multiple of 2 or the addition of 2, so the same rule will be implemented here. Like I can add 17 and 22, after that I can implement the modulus value, or I can implement the mod value on 17 and 23 both, and after that I can add it. The same way it has to be done along with the multiplication also. Like you can see here 17 plus 23, when you add it, it will be a large number. Right now we have taken a very small number actually, but when it comes to the cryptography, we have to play with the very large number. So sometimes it is difficult for us to go manually. So, but I just wanted to show you the example that how the things will work. So 17 plus 23. So if you just either you have two ways, add 17 and 23, implement mod 10, or implement mod 10 on 17 and 23, then add both of it. So if I'm doing it, 17 mod 10 will give you 7, 23 mod 10. That means when I'm dividing 23 by 10, the remainder comes out to be 3. So that's why I'm taking it as 3. So 7 plus 3 mod 10. 7 plus 3 comes out to be 10. 10 mod 10 will give you 0. Same way, if I'm taking 17 into 23, so after implementing the mod on 17 and 23 both, I'm getting 7 and 3. I'm multiplying 7 and 3, which will give me 21. Under modulo 10, 21 will give me 10. So, this is the this is the way that how these things will work under modulo operation. Now, what is the inverse modulo number? I am indicating from the initial of this lecture, very initial part of the lecture, that we have to concentrate more and more on the inverse actually, right? Because every time when we encrypted a message and we just want to decrypt it also, we just need the reverse process. So if we are dealing with the number, so we must understand that what is the inverse of that particular number. See, there are so many things in which we have to get the inverse. Either it maybe in terms of the numbers, it may be in terms of the polynomials, it will be discussed later. But ultimately we have to switch ourselves to the inverse actually. And modulo will be the basic operation which has to be used here. So what is this inverse actually? Before starting this inverse, let me make you two things clear. First one is the identity element, and the second one is the inverse element. That how these things will exist, because once we understand how and when these things will be will exist, then we will be able to evaluate it by the given equation or by some relation. So what we are having this identity and inverse actually. See, what is the identity, right? If I take this word identity in general manner, so what we have, identity means like, if I'm saying that what is my identity, that means I just wanted to replicate myself, right? If I try to implement the same thing on the number, so what this identity will be like, if and in mathematics we are having operations only, so I'm going to consider operation, and any operation whatever I'm considering with any number, say for example a, any number which will give you back the same element after implementing the operation. This is known as the identity. Like if I am having 4, as you can see here on the screen, if I'm having 4, then what number, and I'm talking about the addition, I'm talking about the addition operation. If I'm adding any number to 4, then which number should get added to 4 in order to getting back the 4. So what it would be? 0. That means if I add 4 with 0, so I'm getting back the number 4 again. That means I'm getting the identity. So that for 4, with respect to addition, 0 will be treated as the identity. For any number, not even for the 0, for any number you just consider, you add 0 to any number, you just take it as in general a, you are getting the number back. So it will be treated as the identity element. And this identity, because it has to be considered along with the addition operation, so this identity is known as the additive identity. Same way, if you just wanted to go for the multiplication, so what number it would be that whenever you implement this identity element with the multiplication operation to any other number and you are getting the number back, it would be 1. That means when you multiply 4 by 1, you are getting the number 4 again. So in that case, 1 has to be treated as the identity element, right? So what we are having, like, and 1, if you just consider 1 along with the addition, like you are multiplying 4, you are adding 4 plus 1, so you are getting the 5. So 1 cannot be treated as the identity element with respect to addition. So there are, when you consider the identity element, or we can say that when the identity exists, so it depends upon the operation as well. If you are considering the addition operation, then the identity has to be considered as 0. When you're considering the multiplicative operation, so 1 has to be treated as the identity. So we have to focus on this thing, that what operation we are using. So identity exists whenever this identity will get operated, whatever the given operation we have. Whenever it is getting operated with the number, you are getting the element back. So this is the identity element. In case of the addition, it will be treated as 0. In case of the multiplication, it will be 1. But this is in general. When we go with the modular arithmetic, the things will change. That means it may be a possibility that for 3, the 7 will be treated as the inverse. For 7, the 3 will be treated as the inverse. But inverse is always unique. So for one number, we are getting only one inverse. So the things will work out in a different manner while we consider this modulo operation. But before starting this modulo operation, we must understand that what these things are. So identity element, I think I have made it clear that identity element is the 0 with respect to addition and 1 with respect to multiplication. But in the modulo, it will get changed. We'll see that how the things will work. This is the actually identity. Now, because we are considering the inverse, and before defining the inverse, we should understand what is the identity. So that's why I have defined the identity first. Now, what is the inverse existence of inverse? How you can say that the inverse exists? Because say, for example, you have encrypted any message by using any function or any key, whatever is provided to you. And if you're not able to get the inverse of that particular function, how you will be able to decrypt the message? You cannot. So it's better to understand first that whether the inverse exists or no. If the inverse exists, then we'll proceed. Otherwise, no. There is no point at all to consider those keys or those values, those function, which we can encrypt, but we are not able to decrypt it. So it's better to exist the inverse first. And for defining the inverse, we must understand what is the identity. Because when we define the inverse, so inverse is basically the number. Inverse is, that means the opposite. Right, the opposite. So the same way we have defined the identity with respect to addition, with respect to multiplication. Same way we are going to define the inverse with respect to addition, with respect to multiplication. But the basic funda remains same, that how you are calling any element as the inverse of that particular element. Whenever you are operating these two elements, you are getting the identity element back. Because you know that one is the inverse of the another. So when you multiplying these two numbers, so you must be getting the multiplicative identity. When you are adding two numbers, you will be getting the additive identity. Say, for example, if I'm having any set, right, in which, say, for example, I'm taking 4 again. So which number should get added to 4 in order to find out the additive identity? Additive identity is 0. So when I add 4 to minus 4, it will be giving me the 0 additive identity. So minus 4 will be treated as the inverse of 4. The same way, if I'm considering the multiplication, so what number should get multiplied by 4 in order to get the multiplicative identity? So I must multiply 4 by 1 by 4. 4 must be getting multiplied by 1 by 4 in order to get 1, which is the multiplicative identity. So that I can cross this, cancel this 4 and 4, and we'll be getting 1. So inverse is basically the process in which whenever these two, you are calling B as an inverse of A, whenever you implement any operation in between these two, you will be getting the identity element back. Now, whatever the operation is defined, whether addition or multiplication, the identity has to be taken accordingly. So this is the funda for the inverse. So only inverse will only exist whenever we are getting the identity after implementing the operation in between these two. Otherwise, we cannot say that the inverse exists. So we have to be, very much we must be having a very good understanding of the identity and the inverse, right? Because because inverse, the concept of inverse is coming from the identity itself. So it is very mandate to exist the identity and inverse, whatever the set we are considering. I am again repeating that we are going to play with the numbers, so we must understand that how we are doing it. So this is the concept of the inverse, identity and inverse. And as I told you that while I was defining the identity, that whenever we switch ourselves to this modular arithmetic, so the things will get changed. The same thing happened with the inverse also. That means while we are dealing with the inverse under some modulo, so the things are, again going to be changed. Say, for example, I'm going to define this thing, later, whatever is written here. Let's just take one example here. Like what I'm saying here, that the inverse of 1 comes out to be 1 under mod 5. And 2 inverse comes out to be 3 under mod 5. You can see that I'm not getting 1, 1, 1 everywhere, right? Why I'm not getting? Because, 1 inverse. 1 inverse, when you multiply 1 and 1, so you will be getting 1. So I am saying that 1 is and I'm considering the multiplicative operation here. I am taking 1 into 1, which will give me as a resultant as 1 itself. So that I'm saying that 1 is the inverse of 1 itself. Now, how I'm saying that 3 is the inverse of 2? Because when I multiply 2 and 3, it will be 6. Under modulo 5, 6 equals to 1. That means I'm dividing my 6 by 5 and I'm getting the remainder as 1. So I am getting the multiplicative identity now by multiplying 2 and 3 under modulo 5. So that's why I'm saying that 3 is the inverse of 2. Same way, what will be the inverse of 3? That means what number should get multiplied by 3 under the given modulo in order to get the identity. What it would be, if I'm multiplying 3 by 2, I am getting 6 again under modulo 5, it will give me 1. So that I'm saying that 2 is the inverse of 3. Same way, what will be the inverse of 4? And inverse is unique. So if I have already written that if I'm having, these numbers 1, 2, 3, 4 in a particular set, and if some inverses has been decided corresponding to some numbers, it will not get repeated. This thing has to be considered. So what is this 4 inverse? 4 inverse, what number should get multiplied with 4 in order to get the multiplicative identity, which is 1 under modulo 5. So 4 into 4 will be equals to 16. When you divide 16 by 5, the remainder will be coming out to be 1. So that's why I'm considering this 4 as the inverse of 4 itself. Now let's just come to the definition. What this definition says, that 4 into x is equivalent to, is coming out to be 1 under modulo 7. What it would be? That means what number I should be taking at the place of x, which when multiplied by 4, giving me 1. Right? So this number is known as the inverse basically. How we are going to find out that inverse? Like what things? You can see that 4x must be equals to the multiple of 7 plus 1. Plus 1 because the remainder should be taken as 1. Right? So these things has to be worked like that. We must be having some set while we are finding out this. Like it is written, for example, the inverse of 5 modulo 14. That means modulo 14 has been taken. We are trying to find out the inverse of 5. So if we are considering 5 into 3, it will give me 15. 5 into 3 equals to 15. Modulo 14, 15 will give me 1. So that I can say that 5 inverse, what will be the inverse of 5? It will be 3. So this is the way to find out the inverse actually. So two things are very important here. Identity and inverse. Why we need identity? Just in order to get the inverse. So this I have already explained. Now let's just come to the congruence actually. What is this congruence? Congruence is nothing what we have just done earlier. That means any number whenever is getting divided by the modular value. So whatever the remainder coming out to be, this has to be put in some particular equation. This equation is basically known as the congruence. And this equivalent sign, what you can see here, 3 straight lines, this is known as the congruence operator. So what we have here, like if I just wanted to find out that what value it would be, of 12 under modulo 10. So I am dividing my 12 by 10, getting the remainder as 2. So that 2 is congruent to 12 mod 10. See, we are going to define the congruence equation later on, congruence classes. So we need this notation. So that's why I'm defining it here. And the set can be considered anything. So what we have, like another example, you can see here, there are so many examples written, like 23 modulo 10 will give you remainder as 13. So we are going to write down 13 is congruent to 23 mod 10. So in that way, we can find out the, this congruence classes we are having. Let's just come to this residue classes. Residue, you know that what is residue. Residue can be considered as the left out things, right? Left out in our mathematics, since whatever, since we started the lecture, so left out for us is the remainder. So residue classes will be we will be prepared with the remainders what we have. Like say, for example, I'm having n equals to 5. N equals to 5 indicating I am taking the modulus value as 5, right? So n equals to 5, say for example, I'm having n equals to 5, I'm considering any set Z which consists of 5 elements starting from 0 till 4. Z5 will consist of 0, 1, 2, 3, 4, and 5. I will explain later while I'll go over this mathematics preliminary. Wahan pe I'm going to explain that how to, how we are making these sets. But right now, let's just consider I'm having any set S which consists of 5 elements, 0, 1, 2, 3, 4. And the modulus value, what I'm taking it as 5. So, when I just wanted to find out the residue classes corresponding to all numbers, what is given in the set, it will be like 0. Let's just consider the 0 one. What is this 0 actually? 0 will be consist of all the elements, which will be giving me the remainder as 0 after dividing by 5, right? So what numbers it would be? 0 has to be considered. When I divide 5 or minus 5 by 5, so it will be again giving me like, 0, 0, adding, adding, right? What I'm having, like 0 is the number, 0 may I'm adding my 5, so it will be giving me 5. Under modulo 5, it will again giving me 0. Minus 5 is again the same thing, I'm getting 0. So whatever the numbers, like, starting from 0, giving me 0, 0, 0 after adding, or like, multiplicative group, we have to consider that multiplicative property. Now I'm taking it as the addition here. So whatever the numbers are giving me 0, 0, 0, 0, 0, I'll put all the numbers in the same class. The same way, all the numbers, whatever giving me the remainder as 1, it has to be put in the residue class corresponding to 1. Corresponding to 2, I'm having all those numbers which will be giving me as a remainder as 2 after dividing it by 5, and so on. I'm having these classes. These things can also be, extended with the other numbers. Equivalence relation is, we must have studied this equivalence relation while we were studying that functions and relations. This is exactly the same thing. Like, this thing has to be, when we operate these things in the cryptography, so we need few properties has to be fulfilled. So this equivalence relation will play a very important role over there because it is having very specific properties, which you can see here is the reflexive, symmetric, and transitive. These properties, whenever these three properties are getting satisfied by any congruence class, it will be known as the equivalence class, right? So how it will be, what are these properties actually, reflexive, symmetric, and transitive? Say, for example, I'm having any set S. And the relation R is basically the same thing what we used to call is what is the relation. Say, for example, in mathematics, I'm saying that line 1 is parallel to line 2. So this R is taken as the parallel. The relation what I define in between two lines are the parallel lines, right? So same way, if I'm taking two lines, I can say that line 1 is perpendicular to line 2. So this relation has been taken as perpendicularity. So there are so many ways to define R actually, right? So what we are having, say, for example, I'm having any set S, some relation R is defined, and I am, how I can say that it is the equivalence relation if it is satisfying all three properties, reflexive, symmetric, and transitive property. What these properties says. I'm just going to take one example in order to make you understand, because it's all seems like abstract representation of every property. Say, for example, I'm taking some set L, which is the set of all parallel lines. Now I am saying that L1, that any line is parallel to itself. This property is the reflexive property. In general, I can say that if any element A is related to itself, right? Any element A is related to itself. So this is known as a reflexive property. Same way I'm saying that line 1 is parallel to itself. So it fulfilling the reflexive property. Let's just come to the another property, which is the symmetric property. It says that B is related to, A is related to B is related to R. Commutative property, we know that, right? This is exactly the same thing. So what we have here, if I'm having two lines, I can say that L1, just say for example, first line is L1, second line is L2. L1 is parallel to L2. So quite obvious L2 is parallel to L1. That means the symmetricity has to be followed. So this property is known as the symmetric property. What is the transitive property? Transitive property says that if A is related to B is related to C, then A must be related to C. Say for example, if I'm taking line 1 is parallel to line 2 is parallel to line 3. So quite obvious line 1 will going to be parallel along with line 3 also. So this is the transitive property. When these properties has to be satisfied, then the set considered will have a great application. So this has to be considered while we will consider the this cryptography. Now, what is this? See, because it consists of the few things which has to be used, while we are working out with the cryptography. So this is a very important theorem known as the Fermat's little theorem. And this theorem will give us few results directly related with the prime numbers and with the modular arithmetic, which will be very useful later while we are dealing with the, very long numbers, like very large numbers. What this theorem says actually, this theorem says you are having, say for example, any number A and any number N, right? What is the first thing here? That the GCD of this A and N has to be 1. That means both are co-prime to each other. If the GCD of any two numbers are 1, then these two numbers are known as the co-prime numbers or the relatively prime. So if such condition fulfill, which condition? Like if I'm having any prime M is given to us, and say for example any number A, which is having the power, like like A is having any power, you can see here that 7 raised to the power 2019 has to be calculated here. It's a very huge number, very huge power, and we are going to solve it with the help of the Fermat's little theorem. Fermat's little theorem says that A raised to the power M minus 1 is congruent to 1 mod M. That is what we are having here. If this condition A and M is relatively prime, so there is no need at all to calculate such a huge number. We can write it down directly that it comes out to be 1. How it is going to work here now? Say for example, I'm having any number 7, which is treated as A here. And I just wanted to calculate some power, 2019. I'm going to write it down in terms of M minus 1, where M has to be prime. And the GCD of this M along with A has to be taken as 1. So 2019. When I just implement my division algorithm to see 2019, what I'm going to take actually, it must be M minus 1, right? So M comes out to be, see, the number must be 2018 and sorry, M is equals to 13 here, right? 13 here, and A ki value kitni ho gayi aapki? A ki value 7. The GCD of 7 and this 13 is equals to 1. Let me make it clear again. GCD of A and M has to be 1. I'm going to work out under modulo 13. So M has to be taken as 13, right? And the value of A is 7. The GCD of 7 and 13 is equals to 1. So this condition is fulfilled here. So by the Fermat's theorem, what I will be having? I will be having 7 raised to the power M minus 1. That means 7 raised to the power 13 minus 1. That means 7 raised to the power 12 equals to 1 without doing any calculation. I'm not going to calculate 7 raised to the power 12 here. And because, I know the Fermat's theorem, I can write down this result directly because I have seen that 7 and this modular value A and M both are co-prime to each other. So I know that by this theorem that 7 raised to the power 12 coming out to be 1 directly. I do not need to calculate this value. If you want, you can calculate it. Just try to get that power 7 raised to the power 12. Under modulo 13, you are going to get it as equals to 1. So what I'm having here, like 7 raised to the power 12 by the Fermat's theorem, it seems out to be 1 here. So now I need to calculate 7 raised to the power 2019. So I'm just trying to write down this 2019 in form of the 12, right? So after implementing the division algorithm, what I'm doing actually, I'm dividing this 2019 by 12. And I'm implementing the division algorithm. When I'm implementing this division algorithm, so 2019 can now be written as 12 into 168 plus 3. 12 into 168 plus 3. Now I'm just separating these two terms, 7 raised to the power 12. I think you're getting my point that why I'm trying to do it as 7 raised to the power 12, because by the Fermat's theorem, I already know that 7 raised to the power 12 is 1. So I have just taken it as 7 raised to the power 12 raised to the power 168 into 7 raised to the power 2, 7 raised to the power 3. I have taken it apart because it can't help us out by using this Fermat's theorem. Now 7 raised to the power 12 is 1, and 1 raised to the power 168 is again 1. So we'll only left with 7 raised to the power 3, which will be giving me 343. And under modulo 13, now see, I'm having a very smaller number, you can see. Just compare 7 raised to the power 2019 with 343. It is far smaller number than this 7 raised to the power 2019. So now I'm going to divide my 343 by 13. When I'm dividing it, so the remainder I'm getting it as 5. So I can write it down directly that 7 raised to the power 2019 is equals to 5 under modulo 13. So you can see here that by using the Fermat's theorem, this huge calculation is getting very small. So, these are the, beauty of these theorems. We can take the another example. You can see here that 2 raised to the power 100 has to be calculated under modulo 13, same modulo we are taking here. So, by the same, like you can see here that 100, 13 means, again, I'm taking if 13 is the m. So m minus 1 is 13 minus 1, which seems like 12. So again, I can say it rigidly that any a which is having the power 12, it will give me 1 under modulo this 13. So I'm trying to write down again the power of 2, which is 100 here, in terms of 12 by using the division algorithm. So it must be 12 into 8 plus 4. Now I'm making it as 2 raised to the power 12 because I know by Fermat's theorem that it will coming out to be 1. Now I am having 1 raised to the power n, and this 2 raised to the power 4 is separately. So this will seems like 16 modulo 13, and 16 under modulo 13 will give me 3. 2 raised to the power 100 will be coming out to be as 3 under modulo 13. So this is the use of the Fermat's little theorem, and you will be getting to know that in the cryptography. While I start that, with the basic concepts of the cryptography where it has to be used, I will explain it better. Let's just come to this Euler Totient function. What is this Euler Totient function actually? Say for example, I'm having any set, like in which few numbers are giving. What is the actually, see, whatever the, say for example, I'm having set of integers, say for example 0 to 50. So I am going to consider only those elements into that set which is relatively prime to n, and the number, that means the cardinality of this set, is known as the Euler Totient function. Right? What we have here, say for example, I'm having a set, say for example U9. Can you see that I have taken this as U9? So U9 you're just going to make one set by taking this n as 9. How many numbers are there which is having the GCD as 1 with respect to 9? How many numbers are there? There are these numbers, 6 numbers. 1 is having the GCD along with 9 as 1. 2 is having the GCD along with 9 as 1. Same way, 4, 5, 7, and 8, they all are having the GCD as 1 with respect to 9. So we are going to make this set according to the fact that whatever the element has to be included in that set, these are having the GCD as 1 with respect to this modular value n, whatever is provided to us. So the same way, if you're having 15, n is given as 15. If n is equals to 15, so I'm only considering these numbers which is having the GCD as 1 with respect to 15, right? Say for example, I'm taking 10. So n equals to 10. So how many numbers are there which is having the GCD as 1 with respect to 10? So there are 4 numbers like 1, 3, 7, and 9. There are 4 numbers which is basically having a GCD as 1 with respect to 10. So in that case, what we are going to do, if we wanted to find out that Euler's Totient function, we are going to count that numbers, count that objects, count that, which is coming out to be in that set. So in that case, like if I have taken that n equals to 9, so it seems like 6. So in that case, this Euler Totient function will give you the value as 6. I have taken one more example like 10. So if I'm taking n equals to 10, so I told you that there are 4 numbers, 1, 3, 7, and 9, which will be giving me this GCD as 1 with respect to 10. So in that case, my Euler Totient function will be 4. That means the value of the, the elements, what is available in that set. And it is denoted by this phi n. Phi n it is known as the Euler phi function also. So this is the Euler Totient function. It will be also needed later in the cryptographic applications. This is the Chinese remainder theorem actually. This Chinese remainder theorem has to be used in order to evaluate the inverses actually. And it is a very important theorem also. What this theorem does actually, how this Chinese remainder theorem will going to be worked out. This theorem is basically used to solve a set of congruence equation. Like, we are already aware of that sometimes in our earlier classes, we are having some set of simultaneous linear equation. Like, 3 equation in 3 unknowns. Like 2x plus 3y plus 5z equals to something. So in that case, what we are solving here, whenever we are having the simultaneous set of equations, we are always trying to get the solution of these equations. Solution, that means the common value of x, y, z, which will satisfy all 3 values. Right? This set may be unique or may not be unique. That is another issue. But yes, what we try to do, we are simply trying to we are simply trying to get one set of solution only, which will satisfy all 3 equations if I'm considering 3 equations. So what is the case with the simultaneous equation? I'm having few set of equations. I'll try to find out only one solution for all these equations, which will satisfy the equation simultaneously. So this will be the case with the simultaneous equation. You can see here, these congruence equations can also be, visibly similar to these equations, but the operation is quite obvious, something different here. But yes, you can see here that we are having more than one equation, more than one congruence equation. And we just wanted to find out only one value of x, which will satisfy all these 3 equations, right? So when we implement whatever we are doing in the simultaneous system of equation, whenever we are doing it, in, along with this modular arithmetic, congruence relation and all, so these things has to be treated differently with this Chinese remainder theorem. How these things will going to be worked out, again, I'm repeating because, they all are somewhere related to the cryptography. So cryptography, that means you're going to use computer anyhow, you are going to define some algorithm. So there are, few well-defined algorithm which will give you the one value of x, which will going to satisfy all the equations simultaneously. Right. So what is the case along with the say, if I go with the mathematics, then how the things will going to be changed? How the things will going to be solved? How it has to be done? Say, for example, you can see here, x is congruent to a1 mod m1, x equals to a2 mod m2. And sometimes these values may be similar also, like a1, a2, ak. It may be also that it is a possibility that modular values may be different. These a's are same. Or it may be a possibility, like, but still, like in all the cases, we are going to get x with one x only, which will satisfy all the equations. Say, for example, I'm having this question, what consists of 3 equations. You can see here that x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. You can see here that under modulo 3 and under modulo 7 in the first equation and in the last equation, we are getting the same value too. So it may be a possibility, but still we are going to get one x, which will satisfy all 3 equations in one go. So what is the procedure? What is the solution method? I have written the solution also. This has to be taken along with algorithm also, like, you just put it in some algorithm and you're going to get the result in one go with the help of the computer. But how this algorithm will work, I'm going to define here. Because quite obvious, you guys are not going to do it with, manually. You have to use the computers in order to make such a huge calculation. It is a very small example, so we can do it manually. So what has to be done actually? Let's just try to nominate the given information with some another variable. Say, for example, I'm having the first equation written as x equals to 2 mod 3. X equals to 3 mod 5. So you can see, I have nominated this. See, x is same everywhere. The value what we are getting as a remainder has been nominated as a1, a2 until ak. And the modulus value, what we consider here is M1, M2, and Mk. So we are going to use the, we are going to compare the given equation with this standard one, and we are going to get the value of all these A1, A2, AK, and M1, M2, Mk. So you can see here, what is my A1, A2, A3 here? 2, 3, and 2. Right? What is my M1, M2, and M3 is 3, 5, and 7. Okay. So what we are having, A1 equals to 2, A2 equals to 3, A3 equals to 2. M1 equals to 3, M2 equals to 5, and M3 equals to 7. These values what I have after comparing my given result, given equations with this one. Okay. Now what I have to do, what is the first thing? It has to be operated here, like M. First of all, we have to find out the capital M. What is this capital M? Capital M is nothing. We have to take the multiplication of all the modular values, whatever is given to us, 3, 5, and 7. We are going to multiply 3, 5, and 7, M1, M2, and M3. So when we multiply all three, what we are getting here, 3 into 5 into 7 will give me 105. Is it fine? What we are getting, 105. So when I multiply 3, 5, and 7, I'm getting 105. So the value of the capital M comes out to be 105 here. Right? You can see here that I have written the solution directly, but try to do the same question while I'm while I'm explaining this thing, try to do it by yourself so that you understand that how to get the solution. So I'm taking my M, which is the multiple of all 3 into 5 into 7. So when I have taken this multiplication, it will give me 105. So the value of capital M has been reflected as 105 here. So my main modulus value is 105 here. Now I'm trying to get 3 other values, M1, M2, and M3. The another 3 modulus values. What is the M1? M1 is nothing. The M what you have, getting in the earlier step, it has to get divided by M1. That means when I'm trying to get M1 actually, I should leave that M1 and I should multiply the other 2 modulus values, 5 into 7. So the first M1 what I'm getting is 5 into 7, which will give me 35. M2, now leave small m2, and while you're getting that m2, it will be multiplication of m1 and m3. That means 3 into 7, right? So you will be getting 21 here. How to get m3? In the second step I'm talking about m3. M3 is you have to leave that small m3 in order to get the capital M3, right? So it would be 3 into 5, which will give you 15. So I am having capital M in the first step as 105. In the second step, I'm having capital M1, capital M2, and capital M3, which comes out to be 35, 21, and 15, right? Now what I have to do, I have to get the multiplicative inverses of all these M1, M2, and M3, what I'm getting just in the previous step number 2. Inverses, we all know that how to find out the inverse. We should seek for that particular number, which will get multiplied by this M, giving you the multiplicative identity. You remember that equation? You must remember that equation, what I used to define earlier. Should I show you again? See, this 4x equals to, see, in general, you are going to write down A inverse equals to x mod n, or 1 equals to A multiplied by x mod n. You have to get the value of 1 as a resultant, remainder as 1, whenever this number is getting multiplied with any other number, so that you will be saying that it is the inverse. Okay, so let's just consider the first equation. X is modulus to 2 mod 3, it is given, right? So what I have to find, because my M1 is 35 here. What is my value of capital M1? Capital M1 is 35 here. What number should be there under modulo 3, which will give me the identity as 1? When you multiply 35 by 2, multiply 35 by 2, you will be getting how much? 70. Under modulo 3, it will give you the identity element. So I will be getting 32 as the inverse of 35 point. Can anyone respond me that you get that point, that how we are getting the inverses? Can anyone respond me? We are having so many participants. Do you get that how we are finding out the inverse? Okay, let's just do it. So what we are having here, M1, what we are getting at, the inverse of 35 under modulo 3 comes out to be 2. Same way, inverse of 21 under modulo 5 will coming out to be 1, because when I multiply 21 by 1, right, so it will be 21 itself. After dividing it by 5, I'm getting 1, because 5 into 4 equals to 20. The remainder comes out to be 1. So I'm having as I answer as 1. So the inverse of 21 is 1. Now what we are having here is 15, right? 15, what is the inverse of 15? The inverse of 15 is also coming out to be 1. Is it fine? Right? Every time we are getting it like that. Let me just show you the a solution part actually, because I think you guys are not getting it. Just give me 1 second. Because if you can't see the solution, there is no point at all to get this thing. Sorry. Just give me 1 second, please. Is my screen again visible?
Yes, it's visible.
Yes, ma'am.
Okay, so now you can see that example actually here. I think somehow I'm not able to make you understand that what is this. So let's just take it directly, the entire calculation here. You can see here that all the three equations I have mentioned here is x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Right. So initially what we have evaluated that is that m must be taken as the multiplication of all three modulus values, 3 into 5 into 7. It is coming out to be 105, right? M1 is getting, how you're getting it as m is divided by 3, the first modular value M1. So it must be like m by 3. I told you it must be 35. The second value, what you're getting as 21, and the third value you're getting it as 15. Right? Now, what has to be done? I told you to get the inverses of all these numbers, like whatever the remainder you are getting in the given equation, 2, 3, and 2. Right? With respect to, like you have to get the inverses of that 35, 21, and 15 under the modulus value. Right? So you can see here, now can you see that how you are getting the inverses? Like 35, the inverse of the 35 comes out to be 2, because 35 into 2 will give you 1 under modulo 3. The same way, if you're trying to get the inverse of 21 under modulo 5, so it would be 1. That means when you multiply 21 by 1, so you will be getting 20. Under modulo 5, it will giving you 1. So the inverse of 21 is 1. Same way, the inverse of 15 is 1 here. Now the final solution is given by this equation, a1, a2, a3. We have already separated it from the given equation. M1, M2, M3, we have calculated it, which is 35, 21, and 15. And the last value, you can see here that Y1, Y2, Y3. Actually, it is having some change notation. Otherwise, it is like, see. the x is given as this M inverse. That means all the inverse is what you have calculated. So inverse you have calculated it as 2, it has calculated as 2, 1 and 1. So you're simply putting down all the values here into this given equation. And at last you're getting 233. And under modulo 105, which is the capital M, what you have considered earlier, it will give you 23. So what is the value of x? See, it is clearly written here that the solution of this set of the equation is x equals to 23, which will satisfy all three equations. Even now what you can do, you just simply put the value of x in all the three equations and you can see there all three equations are satisfied. Like just take the first equation. First equation 23. When you divide 23 by by modulo 3, so 3 into 7 will give you 21 and the remainder must be 2. So 23 will be satisfying the first equation. Same way, if you consider the second equation may whenever you are putting this 23 at the place of x, so 23 under modulo 5 will give you 3 as a remainder. So it is also satisfying. Same way, 23 under modulo 7 will give you 2. It is also satisfying. So in such a way, you can get one value of x. Now the question is that what is the application of this Chinese remainder theorem? So, this Chinese remainder theorem is basically able, it used while you are generating the random number, because, whenever you are trying to get some key to encrypt any message, so the random number will play a very important role here. You do not know that, it cannot get predicted, to be very clear. So that's why this Chinese remainder theorem has to be used in that cryptography. Now, in our next lecture, we will get to understand that how these things will going to be used. But for this particular session, only these things has to be considered. So this will be the case while we are, considering. Let me repeat few things for you, that how much we have collected till now. So we have talked, because in my next lecture also these things have to be used somehow while we are considering the mathematical concepts. So these things has to be used over there. So let's just rewind one more time what we had. We have understand that what is the use of the division algorithm. We have done that Euclidean algorithm. I told you that extended Euclidean algorithm is basically used in order to get the inverses, right? This modular arithmetic, I have given you the very basic example for this modular arithmetic, and we have seen that how it will reach till congruence classes and how we are finding out the inverses in that cases, how we are getting one value which will satisfy so many equations at the same time. So these things has to be like we have considered till now. And these things has to be used, again I'm repeating, in my next lectures also, right? Any questions? Any doubt? Should I consider it as no question? Anyone wants to ask? Okay, done. So what we are having in the next one, like we will be continuing with the another speaker, Dr. Srikanth, and he will be discussing about the basics of the cryptography. So, and the lecture will be, we will be having a break of 10 minutes actually. And as according to schedule, we will be meeting at 11:10, 11:15 again for the next session. And he is going to tell the basics about that cryptography. And after that, we'll be considering few more mathematical preliminary, which has to be used for that cryptography. Nihar sir? Dr. Nihar?
Yes, ma'am.
Yes.
So thank you for the session. Actually, Dr. Vinish had a class, so she rushed away. And as you have already informed the participants that we will have a break. And when are we resuming?
After 15 minutes.
15 minutes. So at 11:15?
11:15 is okay.
11:15 we rejoin.
Thank you, sir.
Thank you. Thank you.